If you weren't quite sure how to proceed, don't worry about it. This is a bit of a whirlwind tour of FDTD so that we can do the lab next week. But if you want to learn more about this and more details, there is a follow-on course that you can consider taking, 5340, 6340. So ultimately what we need using the FDTD approach is we need to offset the voltages and currents in both space and time. And here's a diagram showing how they would be positioned if we were to plot them out in both space and in time. The black dots are voltages and the red dots are where we would solve the currents. And you can see that they are each offset by half a grid cell. This would be delta Z over 2 between each of these. And this would be delta T over 2. So this means if we solve the first telegrapher's equations, so this is the first that was on the previous slide, first telegrapher's equation at half integer time steps. Let's think about how that would, if we solve it at half integer time steps, which is right here, this is delta T over 2. So the currents are solved at half integer time steps. If we solve the first telegrapher's equations at each of these half integer time steps, then think about when we apply central differencing to the time derivative, we'll be calling on a voltage that is a half of a time step to either side. So that would be a half a time step into the future and a half time step into the past, which this first one isn't a very good example. They'd probably be initialized to 0, but whatever the voltage is right at time equals 0. And I should probably use a black dot to indicate that. So we're solving for it at this moment in time. We'll be using values that are actually stored in the computer for the voltage. So the way this ultimately looks is that after we start our simulation here at time equals 0, along this horizontal line is time equals 0, and a half of a time step later we solve for all the currents, and then we solve for all the voltages, and then a half time step later we solve all the currents again. This is called a leapfrog method, where we alternate between the two different unknowns. And I can choose any one of these voltages, let's say. I could say this is the voltage at position zk and time step tn. And you'll find in FDTD literature, and also what we'll use from now on, is that there's a shorthand notation for this. We already know that's in space and time, so what we're going to write is in Z and T. So the subscript here will be the case grid cell and or integer spatial location, and the superscript will be the nth time step. So this notation here is just a convenient way to write the voltage at position k and time step n. So finally, after considering the arrangement of the unknowns in space and time and coming up with our shorthand notation, let's now discretize this equation, and we're going to apply central differencing. This is the first telegrapher's equation. And we're going to solve this by applying central differencing. We're going to apply it at half integer time steps. So I'll say that is n, some arbitrary n time step, plus a half to be half time steps, and integer spatial locations k. So putting all this together, on the left we're going to get the current, I'm evaluating this term now, at position k 1/2 cell to either side. So I'm going to have plus 1/2 minus a k minus 1/2, so 1 to either side, and it's going to be they're going to be both at the same moment in time. So this is going to be n plus 1/2 and n plus 1/2. So I'm going to take these two currents at these two moments in space and time. They're separated by delta z, So we're going to divide by delta c, have a minus sign out in front. That's going to be our approximation for the spatial derivative of the current at this location where we're solving this equation. And then on the right-hand side, we have G prime at that location. And we have the voltage, position K, n plus a half, because that's where we're solving this equation. And then we have C prime. And then for the last term, we're going to evaluate this at position K. So I'm going to have the subtraction of 2 voltages at position K. But they're half of a time step into the future, beyond n plus a half. So this is going to be n plus 1. And then a half of a time step into the past. So since we're already evaluating it n plus a half, I'm going to go a half step into the past, so that's going to be n. And then we divide by the time between these two. There's 1 full time step between the two. On the top here is the equation that we just wrote out on the previous slide. So now let's look at all of the terms in this equation and compare them to the voltages and the currents that are stored in our grid. The ones shown in this grid are the voltages and currents that are stored in the computer. So we can, if we need a current or a voltage somewhere, we can only get them at these specific locations where we've decided to store them. We can't get them at other locations. So if you carefully look through all of these terms, have we fulfilled our goal of only using voltages and currents that are stored in our computer, or are there any problem terms where we're calling on a voltage or a current that is not stored in our computer?